okay, you have a technique for force analysis. You have laws of motion, Newton's first, second, and third. You have fundamental concepts, acceleration, mass, and force. Now you need to study particular types of forces, or at least models for particular types of forces. So here's a list. You could pause right now, write down your own list. Forces, what kinds of forces are there? Okay, don't shortcut, pause it and do it. I'm going to do it this way. Forces, vectors, they're a push or pull. There's a strength and a direction. There are types of forces. Some forces are exerted by touching, that is contact. And strange but fundamental, some forces are exerted without touching. We call those non-contact or long range or action at a distance, okay? So let's just look at some that we're going to study. For solid surfaces, there's normal forces. Normal is another word for perpendicular. You've probably seen that in your math classes. There's friction. Okay, so real quick, normal force and sort of a friction along there, something to do with the roughness of the surface. We'll explore that in just a moment. There's fluid drag. You see this here. This certainly is not free fall, and so it can be more or less significant. We'll talk about that in a moment too. Tension in a string. Tension in a string, you pull along a string or a rope, a cable, a chain even. Spring or elastic forces, you've got rubber bands, if you can see that, a rubber band. Test it out. Go up to your friend and say, I just want to test out my physics course, and we'll see about that. There's different kinds of springs. This one doesn't compress, it just stretches. This one compresses and stretches like that. So there's different strengths of springs and elasticity. And there's just a push or pull from your hand. We'll do that real quick and just mention something about that. All right. In terms of non-contact forces, we need to study the force of gravity. So I put a line here because that's pretty much what we're going to usually, as an introduction in mechanics, we stop there. But you can't get away without doing gravity. And it's a really strange little mysterious force, right? Here I have a scale, or I've got another scale which requires that force of gravity, and we counter the force of gravity to measure the force of gravity. We don't even really feel the force of gravity. We feel this contact, and we see for some reason this accelerate downward, but what is that thing? So we'll explore that. There's the electric force. So you've got, of course, electricity, and you've got batteries. And there's a magnetic force. We'll explore that too. Magnetic forces are pretty cool. And the direction on those is pretty weird, but gotta love magnets. There's the nuclear weak force and the nuclear strong force, and that's the list. How many are there? Now, how do I demonstrate nuclear weak and nuclear strong? I'm just going to pull up this piece of equipment and you use some radioactive stuff and nuclear processes and measure it. We won't get into that much in this course, or even too much in your next courses. All right, so those are the forces. Let's explore now some particulars of the normal force, the friction force, just mention fluid drag, and that's where we're going to go. So in this video today, we'll go over here and we're going to look at force from solid on solid. Remember that force is some sort of type. It's from an object. I call it the source object. So if I use S, that's just a thing like me pushing the board on some object. I call it R, the receiver. So the board would be the receiver. Or the board pushes me, and it's the source and I'm the receiver. There's a type. We'll give it a name. There's a strength, also called the magnitude of the force vector, is the strength. And now there's a direction. First thing I really quickly want to say is that if you have any force just from my hand, what do I call that? I mean, you might get into that's a normal force or something like that. I would recommend, just don't worry about it. It's a push or a pull. So FH or force hand or whatever you want to call it. You know, F1, F2, FA, FB, whatever you want to call it. And just leave it as that. If you know the strength, fine. If you don't, fine. you should be able to look at it and decide if it's a push. If it's a push, I think of it as a push away from the source, push it away, or a pull would be pull towards the source. I'm the source of the force. This would be the receiver. I push away, I pull it, loosely. Okay, now let's get into it. Let's talk about the normal force and friction. Okay, keep this straight and it'll go a long ways. Before we do this little table, let's go over here and think about surface on surface, solid surface on solid surface. Okay, kind of like this, or kind of like this, or kind of like this, whatever it is. There's some irregularity on the surface. This is a mechanical model for friction and normal force. There are actually electrical interactions that can occur on an atomic level. You can even have, you might look it up, negative friction. Fairly recent research on that. It's kind of cool. But ours is a mechanical model and goes a long ways. I think it's nice to realize that these surfaces, the green being the one that I'm looking at as the source, and the black being the one that I'm looking. Did I misspeak? The green being the receiver, and the black being the source. So I'm going to choose to see what happens to that. When this surface exerts a force on the receiver, the block, or whatever that is, it can be at an angle relative to the surface. And what we do is break that force actually into a normal force, which is perpendicular to the surface, and a frictional force, which is along the surface. And so keep that in mind. This is perpendicular to S, and this is parallel to the surface S. Okay, so they're really two parts of the same pink force, if you will. But let's break them down, and we'll deal with them separately, as we often do. Okay, let's come back over here and take a look. Normal force. Again, normal is another word for perpendicular, not like, abnormal or strange. Just use the letter lowercase n or F sub n. Some books use capital N. I don't like to because that's the symbol for newtons, the strength of force, quarter pound, right? Leave it in your force table when you do your force analysis. Leave it as a symbol, unless you happen to know, which you probably don't. Leave it. It is not, this is one of the biggest mistakes, just leave it alone. It's not mg. It's not a force of gravity. You'll see that. It's not that. It's just n. Sometimes they will have the equal strength, but that's a special case. N is n. What direction is it? It's just perpendicular to the surface, and it's away from the surface. So let's explore that. The beauty is it's just n. There's no equation. Okay? So for example, let's take a look here. I can choose to look at any object. Let's choose to look at that one. What direction is the normal force on it from the cart? It would be perpendicular to the cart and away from it. Obviously, it's this way. But if I tilt it and make it fall, then perpendicular and away, purple for perpendicular, is this way. And if I tilt it this way, perpendicular and away, that's the direction of the force on this. Perpendicular and away is this way. Now watch what happens. The force from my cart is perpendicular to the cart and away. It's the force on this guy from this contact. Now, the force on this is perpendicular to the surface, because it's the normal part, and away from the surface. And so this feels a force down right now, as you can tell, from the cart. A force down. It doesn't feel me directly. Sure, I'm increasing that force, but you have to take them one at a time. If you're looking at this object, it's only being touched by this object. You may need to analyze more things, but don't put in my hands put in the normal force perpendicular and away, in this case down, from this. Okay, so let's continue to explore it a little bit because people mess that up. It's just N. Put it into your force analysis method, put it in the steps, solve later, don't solve too soon. So I got this. What direction is it? Perpendicular and away. It's not vertical. It's not down, because you don't care. If I look at this surface, then it's got a force into the surface, but I'm not caring about that. I want to know this guy, and people mess this up, so really think about this. The force on this is up, but not vertically up perpendicular to this ramp and away from the ramp, giving it some support that way, but it could slip. If I do this, it still has a force this way, but it slides down. That's fine, because some of that force is vertical, some of it's along the surface. It's this way. Oh, excuse me, some of it's horizontal. So it's this way is the normal force, okay? One more. If I draw a picture, if I go like that, the normal force from the board is out. What happens, it depends. I could have, here's my wall, here's my eraser or whatever, and maybe there's me pushing on it, force hand, and the harder I push on it, the harder the board pushes back. Because if I squeeze it this way, it's got to push back for balance. And that would be the normal force. You can draw it there. Oftentimes we'll take the object and put it there, but we know it's coming from that contact right there. Okay, so be able to do this. I know that the force from this surface here is perpendicular and away from the surface on this object, or you can draw it there, or you can get it out of the way and put it there, as though the tail was attached to it. Okay, just leave it as N. It's not mg. Do not solve ahead of time. There's one. I believe that's good. So that's all there is to the normal force. Friction. Friction F, or uppercase F or lowercase f. Lowercase f is going to mean frequency, but you're going to run into that in a number of places. Capital T can mean tension, or it can mean the period, different meanings. So this is the clearest. It's the force type from whatever on whatever. But people often get tired of writing that and write it like this. Either way is fine. F can be four things for this solid on solid. It can equal 0, which means there's negligible friction or no friction. In some case where there's really no contact, or there's some air track, or maybe you've got some superconductivity going on, or something crazy like that. So it's negligible. A frictionless surface is generally not achieved, but it can be negligible. Or there's no force along the surface. Let me go back over here to this picture. So F is 0 if, for example, this guy is just sitting here and I don't pull on it. Well, then all the surface needs to do is hold it up. And there's no friction whatsoever. The surface just needs to hold it up. And there might be some side-to-side contact there, but they're going to be like that, and net force is 0. So in the case here, there is a roughness to the surface, or even, if you want an extreme case, here there's a roughness to the surface, and yet the side-to-side force doesn't exist. So it'd just be normal. Okay? So that would be when friction is 0. Now, imagine in that same diagram that you start pulling on it. Then you put in, for your friction, Fs, meaning static. There's no equation here. Sometimes it's just this, and again, you have to think physics and think about the process being described. And oftentimes in physics puzzles, things will change throughout the problem. They'll say, and now we're going to tilt the inclined plane more, and now we're going to tilt it less. What happens, etc. So when we deal with Fs, there's no equation. When is that? When it's static and not about to slip. Let me show you that. For example, well, this, let's use this. In this case, now I'm going to push on this. Push here. And it's not really about to slip. I'm just pushing it and push a little harder. You could see it more with a spring. I'm going to pull a little harder, pull a little harder. Now it slips. But prior to that, as I pull a little harder, it's not just about to slip or slide. I can push. I can, again, test it with a spring. Measuring force strength, the spring is pretty good. How much does it compress? I can push, push, push until it's about to slip. But prior to it being about to slip, check this picture out over here again, and we'll see. So as I pull or push, either way, then what happens is I start building up the friction. And that friction would be Fs. And as I pull stronger, then the surface pushes stronger. You know, pull, you can pull a little more, or push a little more, and you get to this place where it just starts to slip. Yeah, but prior to that, there's no equation, right? Just put it in as Fs, if that's the case. Let me show you one more time here. Let's put this one on here. Inclined surface. You can do it. This stuff's all around you. You know this here. So here we've got this guy, and the friction is 0. It doesn't mean there isn't any roughness. It means that the side to side isn't engaged. And now I raise this up. It's not about to slide, but there is some friction. Without it, it would slide. There's more friction. Fs. 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 That's no equation, just, whoa, it did slide. It was right about to slide. I get to that point where it's just about to slide, right about to slide, but not sliding. Right about to slide, not slide. Okay, then go back a little bit, right about to slide, but not sliding. That's different. That's called static friction max. There is an equation for that. So in that case, we're not letting it slide. It will start to slide, then there will be an acceleration. So this is really key. When we deal with just at that breaking point or sliding point, whatever you want to call it, we're going to say that the acceleration is 0. We're not going to let it slide just before. And so what's happened is our friction has grown from 0, and then the side-to-side surface force growing with no equation Fs, right? And then, at that point, when it's just about to slide, but keep the acceleration 0, okay, at least in terms of that sliding direction, then it's static friction max, and there is an equation. It's mu s times the normal force. Let's explore that. So don't always use that. If it's not about to slide, this is the right equation. Otherwise, there's this, and you have to know that. Okay, so let's just quickly discuss this. So this is a Greek letter. It would be written like this. If that's the line on your paper, you kind of have a long front tail like that. It's spelled M-U. You can pronounce it either like a cow, which is the Latin base pronunciation, or mu, which is often the kind of English mu or mu. Either way is fine. It looks like kind of an M, or I don't know, it looks like a U to me, but with a front long tail, whatever it is. That's the roughness factor. That's measured experimentally, so you can look up tables and you can figure out, I've got steel on steel, I got rubber on cement, I got wood, what kind of wood, you know, so it depends on how picky you need to be. If you need to be really picky, you might do the experiment yourself. Um,